Hey, good afternoon, everybody. My name is Wolf, and this is the San Jose Astronomical Association, and we're here today for Streaming Solar Sunday. Welcome to SJAA's online solar astronomy event. This is the third time we're doing this type of online solar event, so I'm hoping that we learned some good lessons from the first two, and this will be smoother than they went before. But either way, I think the last two events were pretty cool, so I hope that you'll enjoy today's event as well. So welcome, especially to those of you who are joining SJAA for the first time. Streaming Solar Sunday, like I said, we're relatively new to doing this online content. We've been moving some of our content online because of the whole coronavirus crisis. Normally we would be having this event, in a place called Hoagie Park in San Jose, and we'd be out there on the sidewalk, and I'll show you what that looks like a little bit later. But instead, we're all sitting here at home looking at our computers, doing it this way, and we can use your help to make this better, beyond what we have today. So I would really appreciate, throughout the talk today or before you leave at the end, please give us your feedback. Let us know what you thought, things you liked, and also things that you didn't like. So we'll see how it goes, and we do value your feedback, and we use that to try to make our content better. All right, here's a little tip for you. This may help you enjoy this show a little bit more. So you're watching this, of course, on YouTube, and we're going to be talking about outer space. Outer space is dark, so you may benefit from YouTube's dark theme. And what you can do here is you can find your little avatar icon, at the top right of your window. You can pull down this menu. There's this dark theme option in the middle. If you click that, then you get this second window, and there's a little dark theme slider button down here. And if you click that, it should switch your window over to dark theme, and you may like that. It's up to you. Give it a shot if you like. This is especially valuable for nighttime astronomy content, right? But still here, hey, we're talking about the sun, but the sun is still out in dark space, so even here, this makes sense. I also want to give a quick, just general announcement here. So going forward, the San Jose Astronomical Association will consolidate all its streaming and video content in one place on this SJ Astronomy channel. Note the hyphen is important. SJ Astronomy channel on YouTube. There is this god-awful URL here, which you'll never remember, right? Sometime in the future, maybe we can make this a vanity URL. For now, don't try to remember this. Instead, what you can do is you can just go to YouTube and you can search for SJ Astronomy with the hyphen, and that will give you the place where, going forward, we're going to try to consolidate all this content. This is all work in progress, that we're doing in response to the coronavirus crisis. So yeah, keep this in mind. If you want to look for content in the future, this is the place we're going to funnel all of our material. All right, so for today, we're going to go through the following materials, right? So we're going to talk about an introduction, then I'll discuss viewing the sun safely. We'll talk about the sun in the solar system. We'll talk about different light as it comes from the sun, something we specifically call H-alpha astronomy. We'll talk about the structure of the sun. I'd like to share some what I think are spectacular sights of the sun. We'll talk about the solar cycle. And then we'll also have a quickie science topic of the month. This is a new segment that we're trying for today. So we'll see how that goes. And as we go through all this, we'll make a couple of visits to my backyard, where I have set up a telescope for us to look at the sun in real time. And we'll also take a few breaks here and there for some Q&A. So please, if you have questions, you can throw them into the YouTube chat, and we will try to address your questions. And if you can't think of any questions, or even if you can, we're going to throw some questions out there as well that you can help us answer, just to get some discussion going. Let me quickly introduce the hosts for today. First, we have Nancy, and let's see. Nancy, you can wave. Thanks, Nancy. So Nancy is one of my partners in crime putting on the solar program. She's been working with me on this for the last couple of years or so, and she's been a great member of the crew. Then we also normally have Rashi here for this online event. However, he's busy right now. He may join us, so I thought I'd introduce him quickly anyway. And if you hear another person pop up later, voice chime in, that would be Rashi. But a new member we have today of the crew is Emery. Emery, do you want to wave quickly? Thanks, Emery. So Emery joined us today, and he's going to be giving the sign topic of the day that I mentioned earlier. So he's going to give us that extra news segment at the end. And then, of course, you guys are stuck with me. Again, my name is Wolf. I'm here running the show for the day. Now, you may also meet Zipper the cat. He is really the master of the house here, but he lets me live here, and every now and then he makes announcements throughout the day. So if you hear a cat meow, that'll be Zipper. Hey, this is basically live TV. These kind of things can happen. I do want this to be interactive. Like I said, normally we do this show on, or in Hoagie Park, right, in location in San Jose, out on the sidewalk, and we're just all talking to each other there, answering questions, whatever topics come up. We can't quite do the same thing here on YouTube, but I would still like to be as interactive as possible. So please, like I said earlier, please ask questions. And as I mentioned already, we'll have some questions for you where you can participate. Let me quickly say something about SJAA in general. So we are an educational organization. We're also a nonprofit. We have a whole bunch of public programs. One of them is happening right now here, the Solar Sunday event. We have lots of other public star parties just this past Friday. We have what we're calling our armchair online star party. So if you did not catch that, maybe look for the next one. I think it was pretty well received. Normally, we also do star parties for schools. So if you have, a kid in school, or if you are a young person in school and you want to have a star party at your school, usually we can set these things up. Of course, here we need to wait until all the COVID-19 stuff settles a little bit. We have public talks. There was one on Mars yesterday that was also shared over YouTube. We provide equipment help and have swap meets, but again, these last two things are again somewhat on hold at the moment. For folks who have formally joined SJAA, now again, all these things I just talked about, they're public, they're free, you can show up anytime you want, doesn't cost you anything. But if you choose to join SJAA for $20 a year, and I always say that's basically like, it's less than I paid for a pizza last week, right? So for the price of a pizza pie, you can join the SJAA for 1 year. That gives you a bunch of additional benefits, like something we call the imaging workshops. We have training for beginners, how to use telescopes, how to find your way across the night sky. We have an equipment loaner program. We have a pretty good library of books, and we also have private observing events. So this is all pretty cool stuff. If you're really into astronomy, maybe give that a try. And like I said, COVID-19, of course, is forcing us currently to cancel all of our public events that we do in person. Instead, we do public events here, on YouTube. Okay, website is sja.net, or you can find us meetup.com SJ Astronomy. I imagine that's how you got here in the first place. So please look there also for future events. And again, our normal location is San Jose Hoagie Park, and we'll actually take a glimpse there in a moment. Yeah, speaking of Hoagie Park, right? So normally that's where we are. Normally what we do is Solar Sunday looks something like this. Here is the sidewalk next to some tennis courts in Hoagie Park, and you see a bunch of telescopes that we have set up and folks looking through that. And it's not uncommon that we have a much bigger bunch of people on the sidewalk than we had at this particular moment when I took these pictures. But of course, today you are the bunch of people, on YouTube. So again, thanks for hanging out with us, during this hour or so. But yeah, so we can't do this in Hoagie Park, but you know what? We can visit Hoagie Park virtually really quickly, and I think that's actually kind of interesting, so let me do that. So here I'm using a program called Stellarium, which is an open source astronomy planetarium application. You can just Google for this and download it for your Mac or PC and or even a Linux machine. And this is a pretty cool piece of software to help investigate the night sky. And what we have here is we have loaded up a background that looks a lot like Hoagie Park. In fact, these are pictures that were taken in Hoagie Park. Here you can see, the tennis court in the background and the grass. And, if we were there right now, we would be probably pretty hot and sweaty because, yeah, right up here, you can see the sun almost right overhead. Now, of course, we're not there, but through this virtual mechanism, we can actually do something that's pretty cool that we could not do if we were in fact in Hoagie Park. What I can do is I can turn off the atmosphere. So I can click a button here that makes it appear as if the Earth had no atmosphere. And look, this is actually really cool. Of course, the sun is still here, but now without the atmosphere, we can see all the other stars that are up there that right now are just invisible because the sun is so bright, it washes out, everything else in the sky, right? We appreciate our blue sky, and it's great, but it hides all this stuff that we could otherwise see. For example, right here, you can see the constellation of Orion, Betelgeuse. Here's what we call the Belt of Orion. So this thing right here is a constellation that we usually think of as a winter constellation, because in the winter time you can see it in the night sky, but right now it's in the summer sky, or excuse me, in the daytime sky, right? And so yeah, it is washed out by the sun. Other things that may be worth noting here is, yeah, notice Mercury is right here, so it's actually very close to the sun, yeah, so I just think this is kind of cool, right? You can do some tricks here where you turn off the atmosphere, revealing all the stars that are up there all the time. We just don't see them during the day. All right. Okay, and we can take a really quick trip to my backyard. And in fact, Haha. You know, this is live TV, so I think something just crashed over there. But that's okay, no problem, we can fix that. Give me one moment. There we go. Yeah, so this right here, right, this is the camera setup that the telescope setup that I have for us here today. So you can see this telescope sitting on a mount. There's a little blue thing stuck in the back. That's a camera. We'll talk about this a little bit more later. But yeah, so this telescope is already out there, and it is slowly tracking the sun as the sun is moving across the sky. So yeah, we'll get back to this, and we'll actually take a look through the telescope in a little bit. Before we do that, though, I want to make sure that we're really clear that we do not want to look at the sun without proper eye protection, right? The sun can be actually quite dangerous if you stare at it directly. So when we use telescopes to look at the sun, we have to take some special measures. Here on the left side is one example of a telescope that you might use during the nighttime. You know, this opening here on the left side is what we call the aperture. Whoops, excuse me. It's called the aperture. That's where the light enters. The light goes then through this tube and it pops out the back here. You know, this is the eyepiece. That's where you would put your head to take a look at the picture. Now, if you point at this telescope at the sun as it sits here, as it's shown right here, boy, yeah, we would turn into a smoking, smoldering crisp right at the other end because the sun is just so powerful. So instead, what we need to do is we need to put a solar filter on this telescope, and that's what this disc is here. So in this case, yeah, this telescope has been protected with a solar filter. Here's another example of this, similar type of telescope, and you can see that this filter has been attached. And yeah, you may notice that the filter looks like it's just some kind of a foil, and it is in fact in this case. So it's essentially a mylar film. It's very thin, it looks kind of flimsy, but it actually does the job of protecting us against the sun. There are also filters like this that are made out of glass. There's a few different varieties, but these foil filters are actually quite popular and effective. You can also get filters like this for binoculars, the same idea, right? Do not look at the sun with binoculars. You will damage your eyes probably irreparably. Instead, you can use solar filters like this and make it all safe and fun. And if you look at the sun with your naked eyes, you know, you can use these kinds of protective glasses that are very popular during solar eclipses, right? When we had the solar eclipse a few years back, you know, these were all over the place. And so, yeah, so here, you know, you can see all these folks, they're have their glasses on, looking at the sun. Here's a girl who very wisely is not looking at the sun because she's not wearing her glasses, right? So yeah, please make sure if you do want to check out the sun, always use proper protection for your eyes or for your photographic or telescope equipment. Okay, very important. All right, having that out of the way, let's take a look at where we are in the solar system. So I like this picture because here, you know, the sun is huge, sitting in the middle, and then it's showing us our planets going outward. Here's Mercury, Venus, the Earth with our moon, then there's Mars, then there's the asteroid belt here, and then we have our gas giants going farther out. There's Jupiter, Saturn, Uranus, and Neptune, and actually here's a little comet in the drawing, which is kind of cool because right now there is a comet in the sky. There's a comet Neowise that's visible in the night sky in the mornings, I think around 4 a.m. I have not seen it yet, but I'm not usually a morning person, but I think I may actually get up to try to check that out, and you may want to do that as well. So yeah, this is kind of a cool picture, but it is an artist's rendition. This is really all wrong in terms of scale. It does not accurately show the size and spacing of these objects. And so this next picture is much more accurate. And I realize you have a hard time seeing anything on here, right? But yeah, so here at the very left end is kind of a sliver that represents the sun. Then you may see some faint little dots here. Mercury is kind of right here. It's almost too small to really see at all. But then you see tiny dots that are Venus, Earth, and Mars. Then the asteroid belt is here. Jupiter is definitely a respectable circle, although still small in the grand scheme of things here on this slide. And you can see Saturn and so on. Pluto is somewhere out here. It's too tiny to see. So this representation here is a much better view of the relative distances and sizes. You know, it's just good to keep that in mind. It's really hard to draw the solar system to scale and make it look interesting. So that's why we end up with pictures like the prior one. But here, you know, this slide where things are really hard to find, that's actually a better representation of the solar system. There's a lot of empty space out there. So let's ask a quick question here. How do we see anything, right? So we look at stuff and we see things. How does that work? Well, we see things through light, right? So, you know, things emit light, we see those, and then the light also bounces off other stuff, you know, that's how we see those. So right now you're seeing me because there's light coming in the window, it's bouncing off me, it's hitting the camera, and then that's being transmitted over, to your computer, right? But it's all light. And let's think about light a little bit more. Here's a couple of pictures I took, I think it was a year ago or so, of just rainbows. I think rainbows are just really pretty. I imagine most of you would agree. But they actually embody some pretty interesting science, right? So here we just have the pretty rainbows, but you may remember something like this even from high school physics, right? So here is a white light beam that's entering this prism, and then the prism is splitting that light into the various colors. This is exactly the colors of the rainbow. And so if we look at that in a little more sciencey way, it looks like this. So light is part of the spectrum of electromagnetic radiation. Radiation sometimes sounds like a scary term, like, ooh, radiation, right? It sounds dangerous. But actually, we're very familiar with radiation. It's everywhere. We rely on it in many ways, right? So we certainly know radio waves. I mean, it's now the internet age. Most of us listen to things on our iPhones and podcasts, but FM and AM radio are still things, right? You can still certainly tune into radio broadcasts like you see here, AM and FM radio waves. You use your microwave oven, right? So we use EM radiation to heat food. IR here means infrared. That's the kind of radiation that you feel as heat if you're outside or even inside, right? Then here, this little sliver of the electromagnetic spectrum, this is the part our eyes can detect. So we can see part of this huge electromagnetic spectrum, but the part we see is only this tiny, tiny little sliver that is the colors of the rainbow. And beyond what we can see is the ultraviolet range of light or electromagnetic radiation. That's the part that gives us sunburn. Be careful with that. And then we have X-rays, and then finally gamma rays are very energetic electromagnetic rays. And these things are certainly dangerous. They can kill us, but luckily, lots of things around nature end up protecting us from gamma rays. So this is the complete electromagnetic spectrum, and the part we see is just this tiny little part. Point of interest, is actually so some animals, other than us, right, can see other colors that we cannot see. So there are insects and some birds that can see colors that our eyes cannot detect. So, our eyes just happen to do this. Other living critters on this planet can actually see things that we cannot see, which I think is cool. But we can use our technology to see these things, right? So we could use technology to see UV light. We can use technology to see infrared light and so on. So we have certainly learned to augment our limited eyes with technology. And so that takes us to this poster, which is something we usually have out in Hoagie Park, and we can use it to kind of kick off discussions. I realize there's a lot going on here, so let me kind of walk you through this step by step. So first, let's focus on this part over here. So here's an image of the sun, and it's labeled photosphere. The photosphere is essentially what we consider the surface of the sun. Now, the surface is not a rocky, the sun is not a rocky world like the Earth is, right? So you couldn't stand on it. It's not hard. But we still consider it the surface, and it's the part that emits most of the light that we end up seeing. So this is the photosphere. This is what generally appears bright white if you were to look at it right now when it's up to the sky. Again, please don't look at it, not without proper eye protection. But then in the evening when the sun is setting, this is what we basically see as, kind of the yellow-orange ball hovering over the horizon. And sometimes this thing reveals things called sunspots, which you can see here, and we'll talk about sunspots a little more as we go through the next 90 minutes or so. Okay, the next one here is labeled chromosphere. So this is the same sun that we just saw in the photosphere picture, but it is we're investigating it with different technology, right? Focusing on a different part of the light. And what we're seeing with this is essentially the atmosphere of the sun. So we have the photosphere, we said we called that the surface, and then above the surface is an atmosphere of sorts. It's rarefied hydrogen gas, and that's what the chromosphere view reveals. And you can certainly see some structures and textures here, right, that did not appear in the prior view. And we'll talk about these structures and textures more on subsequent slides as well. There are things here that we refer to as prominences and filaments, we'll define that further. The next layer out, again, this is kind of the next layer of the atmosphere, is what we call the inner corona. Again, you can see things here that did not appear in the prior views. Now, unfortunately, this is a view that we cannot realize from the ground here because the atmosphere we live under blocks the UV light that was used to take this picture. So to take this kind of picture, we have to use a satellite. We have to, send a probe out into space and, use that to look at the sun. Finally here, this is the outer corona. So this is the outermost extents of the sun. And this stuff that you see on the outside here, this is something that we can only see when the sun is actually in eclipse. Now in this particular picture, it's a composite. So really the corona was photographed when the sun was in eclipse, and then whoever made this picture that actually plopped a picture of the sun in the center. But you would never actually see it this way. Later on, I'll show you a couple of eclipse pictures where you will see what this really looks like. The key thing is that the outer corona, even though it extends way, way out there, it is very, very faint compared to the bright disk of the sun. So when the sun is shining, all this stuff is washed out and we don't see it. Only when the center of the sun is blocked, will the corona pop into view. But this is a great, cool thing to see. If you have a chance to see a total solar eclipse, go for it. This is awesome. So here's a representation of just other views of the sun in different kinds of light. And we don't have to look at this in too much detail. The key point here is that, in science, we use lots of different instruments to look at the sun, or other things for that matter, in different ways. And by looking at things in different light, by focusing on different parts of the EM spectrum, we can reveal different details and learn different things about the objects. So, the key takeaway here is, these colors are kind of false colors. Most of this light we cannot see. We've seen it with instruments instead. But the key is that all these pictures look a little different. So with every one of these pictures, we're revealing a little bit of different detail that we otherwise would not be able to see could we not filter and isolate all these individual different colors. All right, and with that, let's take a moment here and see if any questions have collected. Has anything popped up from our chat stream?
No, our audience is just very focused into your presentation. I think they listened to everything you've said.
I hope that's true. I guess if they're snoring, we can't hear it. So, okay, we'll go with your explanation. I like it. Okay, well, if you don't have questions, we can fix that, though, right? So, as you can see in my slide, and next to Nancy is this game wheel, right? And so Nancy is going to spin this for us, and we're going to generate a question and see if we can have some fun with it. So this is primarily a question for you. So what I would like is, so Nancy's going to ask this question, and then, give it a shot. See if you know the answer. And, you can just shout it out into the chat stream. If you don't, maybe take an educated guess, but just give it a shot. So this is our intent. Our goal here is to try to generate a little bit of interaction. So Nancy, give it a whirl, please.
All right, let's go. Question number 1. Let's see what category.
Okay, we got the red one. It's an F.
Yeah,
okay.
F. Okay. So... Oh, this is an easy one. You're going to get this one. So the sun hasn't always existed. Scientists estimate that the sun is about how old? So how old is the sun, in other words? Easy.
Okay, good.
Okay, I'm going to do one more question. How's that?
Exactly. So while Nancy's spinning, so while Nancy's spinning, go ahead and punch your guess for this, or actual answer, if you're not guessing, please into the YouTube chat. Meanwhile, Nancy's going to give a second question for us to think about.
Yeah, let's do one more question. Look at the answer.
Okay, we like red today, apparently. All right,
Okay. So section A. Okay, this is a good one. I like this one. How close is the nearest star to us?
Okay.
That's not the sun. We're not talking about the sun here, okay? So how close is the nearest star that's not our sun?
Yeah. So there's actually an important implicit point here, right? So Nancy kind of said it, but it's not necessarily obvious to everyone, right? So our sun is a star, right? So at the nighttime, we see lots of stars in the sky. In fact, we can, there are even stars up there during the day, like I showed you a moment ago with the, Stellarium app. So our sun is also a star. It's just the star nearest to us. And then, so after that, what's the closest star to us? Okay, did we get any answers roll in to the first question?
Not yet. Come on, people. This is an easy one, everybody. Give it a shot. How many thousand years?
If you expect us to do all the work here, you guys are wrong. Come on. We need your help. You're going to make me give the answer.
Question number 2. It's an easy one. We're going to have to bribe these.
Okay, next time maybe we'll have to we'll have to promise to email people some candy bars or something, right? For correct answers. Maybe we'll do that. All right. Well, do you want to give it away then? Let's see. So what about the age of the sun?
Okay. So it's about 4.5 billion years.
Yeah, okay, million, billion. Yeah, billion is the one, right?
Billion.
It's easy to get that first letter off. But yeah, it's about 4.5 billion years old, and the Earth is around that same age, right? So the sun formed, and the Earth and the other planets formed shortly thereafter, shortly in astronomical terms. So yeah.
Okay.
So, and the universe is about 13.8 billion years old, right? So the sun is, yeah, so it's maybe a third of the age of the universe, right? That the sun has been around.
Okay. So actually, I have a few answers too. Bill says the sun is approximately 4.5 billion. Yay.
Yeah. Okay. Okay. We'll email you a candy bar later somehow. Okay, so.
I also have, I think Ila Sensei also said 4.6 billion.
Okay. Good. Thank you.
There we go. Yeah. Let's see. I have Spencer says nope. Okay. So this is the next question. Answer to the next question. Mm-hmm. I have a few answers here. First one, I have Spencer says the moon. Okay. The question is how close is the nearest star that's not our sun? Mm-hmm. Okay. So first answer is the moon. I have Rajesh, who says Alpha Centauri. Mm-hmm. That's 4 light years. I also have Marian said Proxima Centauri at 4.2 light year.
Yeah. Okay. Exactly. So this one is a little fuzzy, right? So Alpha Centauri is a star system that you can see from the southern hemisphere. So we cannot actually see it from our part on the globe, right? But we could go to Australia, and then at the right time of the year, you could make that out. And then, we've discovered a star near Alpha Centauri that we now call Proxima Centauri. It's a companion over there, right? It's part of that system. And it's actually closer than Alpha Centauri, but it's much fainter, so it's much harder to see. So so the technically correct answer is Proxima Centauri, although we'll take Alpha Centauri. That's in the right ballpark.
Yep.
So, yeah. Cool. Thank you guys.
We got answers.
Okay.
Perfect.
I appreciate it. Thanks.
Do you have anything else to add?
Well, I think that's it for now. So let's go ahead and move on.
Okay.
Thank you. Okay. All right. So let's see. So here's the sun again in the sky, right? And I said earlier, we talked about the photosphere. We said that's the layer or kind of the surface of the sun that's emitting the light that we see. So so when we're looking at the bright sun in the sky, we're essentially looking at the photosphere. Okay. Now, then I also showed the chromosphere earlier, right? And I said this is kind of the inner layer of the atmosphere of the sun. And this is something that we cannot easily see unless we employ a little bit of science, right, that goes back to the electromagnetic spectrum and the rainbow. So let's talk about how we get to visualize the chromosphere. So we all know the moon is made of cheese, okay? So let's not argue about that. But the sun is a different question, right? So what is the sun made of? Well, it's made of one of these things, right? So you may remember this table from high school chemistry, or who knows, maybe we even have some chemists and scientists in the audience. So so this table is a summary of all we call the natural elements, or for that, not just natural, there are even some synthetic ones here that we've made in the lab, but these are all of nature's building blocks, I should say. I sometimes call these nature's Lego blocks. They're essentially the simplest building blocks that we encounter every day from which everything else is made. You yourself are made from building blocks on this table. Okay. And the simplest building block on this table is this guy here, the H, the hydrogen. And it turns out that that's what the sun is made of, right? So the sun and other stars start out being made out of hydrogen. And over time, they burn this hydrogen into helium, which is the thing over here. That's what party balloons are filled with as well. And so then, suns have their life cycles where they consume their fuel and stuff happens. But stars start out as being balls of hydrogen, and that's what our sun is as well. And so our sun is not made of cheese. Our sun is made of hydrogen. And so now let's talk about the hydrogen spectrum. So here's the rainbow again. So we've seen this a few times already. But now let's think about hydrogen gas specifically. It turns out if you take hydrogen gas, or for that matter, any other thing on the periodic table that we just saw, and if you energize it or heat it up basically, and you cause it to glow, it will glow in very specific colors, right? So it won't just be, all white light or something. No, you will actually get a very specific effect. So hydrogen will, in the visible range, so in the range of this rainbow that we know how to see, it will glow with this purplish color here. This is at a wavelength of 410 nanometers. It will also glow with this blue. It'll glow with this guy, and it'll glow with this red over here at 656 nanometers. So when you energize or excite hydrogen gas, this is specifically what you end up seeing, right? You see exactly these four colors. Okay, it's precisely these lines. We call these spectral lines. And then, yeah, we've given this red one here a specific name. We call this hydrogen alpha, and that's the most interesting to us today. Just for comparison, here are some other elements, helium, oxygen, carbon, and each one of these you can see has a different pattern of lines that light up when this element is energized or excited. And just as a really quick aside, this is amazing because this means we can look into outer space, right? We can look at things that are incredibly far away. We'll never get there. We can never visit those places. But by analyzing the light, by analyzing this bar pattern, it's like a barcode at the supermarket, right? By analyzing this barcode, this bar pattern, we can tell exactly what stuff is made of, even though it is incredibly far away. We could just analyze the light, and we know that, hey, for example, there's oxygen up there or whatever. So, okay. So yeah, so now we're back to this hydrogen alpha spectrum with the the hydrogen gas spectrum with the hydrogen alpha line over here. And we have telescopes that you can buy one for yourself that isolate specifically this color of red. They throw away everything else and they just highlight this hydrogen alpha spectral line. And yeah, so here's a couple telescopes that do this. This is an example. It's called the Lunt, that's the company, and it's called an LS100 THA. Basically means it's a 100 millimeter lens opening. It's a 100 millimeter aperture telescope. For comparison, here's a smaller version of the same kind of thing. This is a 50 millimeter telescope. It's less expensive, it's smaller, but can still give you pretty amazing views of the sun. And actually, to help me, maybe as a plug for SJAA, I said earlier, if you choose to, spend one pizza's worth of money to join the SJAA, you can join the loaner program, and then you can actually borrow one of these telescopes. This is our loaner kit. So this kit is available for checkout to SJAA members if you want to do your own solar observing with an H alpha telescope. And just for completeness, I want to point out that in the prior slides I showed some Lunt products. I'm not trying to pitch Lunt telescopes in any particular way. So just for completeness, there's also a company called Coronado that also makes solar telescopes. And the one at the top left here is called the PST, or Personal Solar Telescope. This is probably the least expensive telescope that you can pick up if you wanted to invest in an item like this. But all of these telescopes go for that hydrogen alpha spectral line that I described a moment ago. And you guys are probably hearing the cat. See, I warned you guys that we might have a special guest, and I think you can hear him meow. So he's participating today. All right, so for today, like I said, we're using a Lunt 100 telescope with a feature called double stack. If you're wondering what that means, you can ask about it in the chat. I'm happy to talk about it. For now, I'll just blow past that though, and I'll tell you that, yeah, normally you put your eyeball right here, right? So this is normally the place where the eye goes and you look through. Instead of putting our eyes there today, we have a camera attached to it. And today in particular, I'm using something called a Malincam DS16C astronomy video camera. So yeah, just for those of you who are curious, that's the equipment for today. And then yeah, so going back to this chromosphere picture, right? This was a NASA picture taken in H alpha light. Okay, and then down here is a picture that I actually took back in 2017 with my own setup and that camera you saw on the prior slide, and you can see, there's some cool features here as well. This picture is not as fancy as the prior one because it was just a snapshot as opposed to fancily processed, but still kind of cool. And having said that, let's go check out the backyard and see what's going on. Okay. So what's happening here is, let's see, so the sun is actually crept out of view a little bit, so the telescope is trying to track the sun, but it's standing actually on a wooden deck that's kind of wobbly, so, the things are not necessarily staying where they're supposed to be. So let's move the telescope and we'll pull it back. Okay. Oops, I hit the wrong button. I hate it when I do that. Let's go the other way. Okay, all right. Okay, and it turns out that actually at this time, it's hard to find fancy features on the sun, and I'll explain more why that is later. But we can actually see a few things here, right? Notice, so first of all, let's see. So what you're seeing here, this is the sun. Obviously, it's not the complete sun. Part of it is right now sticking up beyond the size of this window. But before we scoot around some more, I want to point out that, yeah, notice down here, you kind of see something sticking out, right? There's like a little tongue sticking out, and there's a feature over here as well. So these look small, but you could fit 109 Earths across the diameter of the sun. So even though these things look small, they're actually pretty big compared to the size of the Earth, right? Even these quote unquote tiny things, could swallow up the Earth without that much trouble. So yeah, these are eruptions from the outer layers of the sun, eruptions within the chromosphere, right? And we call these prominences. So when you have one of these eruptions that glows in the hydrogen alpha light, kind of sticking out from the edge of the sun, we call those prominences. And you can see a small one here and a small one here. Notice also that if you look inside the disk of the sun, excuse me, you can see there's some texture here, right? We can actually play with this a little bit and see if we can make the texture show up a little bit more or a little bit less. I don't know. I can often think of the sun as kind of looking a little bit like an orange, right? So you can see some texture here that's a little bit like an orange skin. And that is real texture on the sun, essentially. So, and if we had Rashi here, Rashi would probably have an orange to show us. I should have had an orange ready, but I only had apples in the kitchen, and that just would not have been the same thing. Okay, so here now we're scooting around a little bit, looking at other parts of the sun. So as I'm pushing these buttons, the telescope in the backyard is actually moving a little bit. And so one thing that's interesting to note here, there we go, yeah. So here you're seeing, let me change the exposure a little bit to make this maybe a little easier to see, yeah. So you can see some dark parts here. This looks like there's a scratch on the sun, or sometimes I think of it like a little scar, right? And there's also, you can also see some marks here in the sun. So it's not all uniform. You certainly have that orange skin texture everywhere, but somewhere that orange skin texture is kind of interrupted by these little dark spots. And by the way, notice that there's another little nub sticking out here, and you can actually see some wispy stuff up here. It seems to extend out quite far relative to the ones we saw on the bottom. But they are kind of faint. But let's see if we can maybe pull those out a little bit more. Let me scoot down a little bit. Okay. Okay, maybe we can turn up the brightness a little. Oh, too much. Okay, there we go. Yeah, so here you can kind of see some stuff sticking out, right? So here, this almost looks like a little loop or arc. And here something sticking out as well. And again, these things look small, but like I said, keep in mind, right, that my little grabby hand is maybe roughly the size of the Earth, right, compared to the sun. And so, yeah, so even though these look small, they're actually quite respectable in size. And so these things on the edge, we call these prominences, okay? And then the thing that I earlier referred to as a scar, we call those filaments. And it turns out they're just two different names for the same type of phenomenon. So when you see it on the edge, like we just saw here, there's like a loop or an arc, and I realize now it's harder to see, right? But you remember this loop or arc that you saw, and it's on the edge, so we see it, well, edge on. But when you have one of these filaments here, they're the same type of structure, but instead of being on the edge, they're kind of going towards us, right? So they're within the disk of the sun, and as a result, they look like a dark mark, like a scratch. So if you imagine this in 3 dimensions, and of course it really is all 3-dimensional, yeah. So here, there's really something that's kind of sticking out towards us. And I'll show some more pictures that will make this more clear. Okay, so with that, let me go back. We'll check in on the backyard a little bit more later. Okay. But actually, yeah, let's take a quick question break here. See if the last stuff we talked about generated any new questions. And also,
all right, we actually. Okay, so my turn then.
Go ahead. Yeah, please go.
Yay! So we actually have a couple of questions. First one was asked by Spencer. How do we know what other galaxies look like? And Marianne did a wonderful job answering that question. She really gave examples and the detail. Thank you so much, Marianne.
Okay. Yeah, thanks. And let me just add something to that, I guess. So since Marianne already answered it, yeah, I'm not going to go through it again. So again, thanks, Marianne. But if you also want to hear more about this stuff, so next Friday, we give other public events, like I said at the beginning. Next Friday, I'm doing something I call Sights of the Cosmos. It's an introductory talk in astronomy. There are lots of different ways to introduce astronomy. But during that talk, I'll also talk about galaxies some more. So if you're curious, you could check that out, and maybe, we can go in more in depth with that kind of a topic and question. So, sorry, Nancy, go ahead, please.
No problem. The second question is from Lori. Are the different spectral colors for hydrogen depend on different ions?
Depend on different ions. Not exactly. So this will be a short answer, right? Because the long answer could easily take us off into the weeds. Although it's a really good question. So you have your hydrogen atom, right? So an atom is essentially a nucleus which consists of protons and neutrons. In case of hydrogen, the simplest thing is just one proton in the nucleus, and then there's an electron that's paired with it, right? So you have one hydrogen atom is a proton in the nucleus, and one electron that's around it. And classical picture usually represents the electron like it's orbiting the nucleus, kind of like a planet orbits the sun. So that's a common way to draw it, but that's actually not correct. We really end up in a realm of quantum physics, and you've probably heard that term. And quantum physics is complicated. I'm not a physicist. I don't really understand it either. But I'll tell you that what generates the particular spectral lines is that electrons can have only certain particular energy states, right? So there's a place where the electron can be in its most restful state, if you will. And then if the atom is somehow energized, if we give it energy in some way, that will elevate the electron to a particular other state, and can only be one particular next state. That's the quantum part, right? It's not continuous. There's a step there. And there's different types of steps depending on how much energy you pump into the atom. And so as you pump energy into the atom, the electron bounces up to its higher energy states, and then eventually the electron will fall back down, and it's falling down the exact same quantized distances. And every one of these falls corresponds to a particular energy in a particular color. So each one of those spectral lines corresponds to a very particular transition of the electron between one energy state and another one. I don't know if that made sense. That's kind of the short version of the answer. And actually, I should maybe point out, in the picture I showed earlier, we just saw 4 spectral lines. Those are just the ones in the visible range. There are actually a lot more, but they are outside the visible range. We need instruments to detect them. So the hydrogen atom actually has lots of possible energy transitions for its electron, and they result in a wide array of possible spectral lines. So I hope that made sense. So, at least for a short answer now.
Okay.
Was there another question?
No, that was it. And
okay, cool.
All right. So how about if I give our viewers a couple of questions?
Yeah. Okay. Let's spin a couple more. Throw a couple out there. Then I'll show a short video while they think about the question, and then yeah.
Yeah. Okay. So it's in category I. Oh, okay. Now, this is a good one. What is a solar flare?
Oh,
you guys
okay.
Listened to Wolf earlier. You probably can answer this easily.
Well, actually, I haven't quite defined a solar flare. This is actually a little trickier. This question may be trickier than you think, but give it a shot. Yes. Okay. Go ahead and give us our second question. Mm-hmm. Oh, you got a J.
J.
All right. Yeah.
Okay. Let me bring up the J. Okay. Okay. What would happen if the sun, with all of its current mass, would turn into a black hole?
Oh, that's a cool question. All right. Great.
Okay. So,
right.
Yeah, think about that. I think Wolf has a little video to show. And once that's finished, we should give you some time to think about the answer. And please post the answer. We'll go over those.
Exactly. So what we'll do a short video of what I call the size comparison. Yeah, while we show that, think of these answers. So here we go. So I like this video because it really illustrates again how big things in space really are. We really don't have a concept for much of this because we're just used to our everyday world. You know, we see trees, we see cars, but you know, we really don't think about how big some of these things out there get. So we start out with the Earth's moon, you know, something we're certainly familiar with. There's Mercury, then we go up to Mars. You can see Venus. Okay, the next jump will be Earth. And Earth is not that much bigger than Venus, actually. But then we make a big jump. Here is Neptune, Saturn, you know, Jupiter. And notice Earth is getting pretty small. In fact, we just kind of lost it there on the left side. But yeah, here's our sun, and the Earth is back in the frame, but now the Earth is basically a pixel and we can't really see it anymore. Sirius A is a star bigger than the sun. Here's Pollux, a star even larger than that. It's called an orange giant by classification. Arcturus, this star is currently visible in the night sky almost overhead. Aldebaran, a red giant. And notice our sun is almost lost at the bottom left now. Rigel, a blue supergiant. Holy cow, look at this, something called the Pistol Star. Antares. And again, keep in mind where we started, right? So you know, our Earth has been lost long ago. Even our sun has been lost. And here, the largest known star, you know, is just huge. So I just think this is actually really amazing, right? So I think this puts into perspective how large our sun is. Actually, not that big. I mean, it's really big compared to the Earth, but compared to some of the largest stars out there, it's almost like a grain of dust. So that's pretty impressive, I think. All right. So where are we with our answers?
Okay, let's take a look. Let's see. Okay, I have Mary answered the question of solar flare. It's
Okay.
an eruption. Okay, it is an eruption on the sun, like a volcanic eruption on Earth.
Ah, okay. Okay.
Pretty cool.
Okay.
And I have not received any answers to question number 2 about what
second
would
one?
happen if the sun. Yeah.
Okay.
Yeah.
Okay. All
Any
right.
more attempts?
Okay, well, think about the black hole for a moment, I guess, while I say something about the first one. So solar flare is a little tricky question, actually, right? So earlier I showed you something I called a prominence, right? And we'll see more examples of prominences in a moment. Often people call a prominence a solar flare, and that's technically actually not quite right. So one reason we have this question in our game wheel is because, yeah, it's kind of important to separate those things. So a prominence is not a solar flare. However, a prominence can turn into a solar flare. So we'll talk about this a little bit more later, but yeah, the prominences are driven by magnetic fields, very strong, large fields sometimes. And then you can have a case where these strong magnetic fields abruptly reorganize. It's almost like a rubber band snapping. And when that happens, a burst of energy is released, and that release of energy would then be the solar flare. Yeah. Okay. And no takers on the black hole?
No take on the black hole.
Oh, okay. Well, okay. Maybe the good news there is that nobody thinks we would just get sucked in. That's kind of a common misperception, right? You know, black hole sounds scary, kind of like the word radiation sounds scary. And not to be, you know, I don't mean to take it too lightly. Don't get too close to a black hole. That could be bad, right? But actually, if our sun were to turn into a black hole with the same mass that the sun currently has, almost nothing would happen. I mean, certainly the Earth would just continue in its orbit. We would just keep going around what used to be the sun and is now a black hole. So black holes don't just suck, right? They have gravity just like everything else. And the gravity depends on the mass. And whether the mass of the sun is shaped like the sun or whether it's shaped like a black hole actually has almost no direct implication on our orbit. We would just keep orbiting. Now, if the sun were to turn into a black hole, that would be bad because tomorrow there'd be no daylight. That would be really unfortunate for us. But the key point here is, yeah, so turning the sun into a black hole doesn't mean we would just get sucked in, right? We would just continue to orbit, and so would the other planets as well, actually. So.
Okay.
Okay. And
so,
now I forgot the other, yeah, there we go. Right? That was the second question. Yeah. Okay.
Okay. So for question number 1, I have to go back to question number 1 for a second.
Oh, sure. Please, yeah.
I have a follow-up question for that, for the solar flare. Rajesh asked, solar flare starts at an explosion close to the center of the sun, correct?
Close to the center of the sun. Not quite. Let me table that question for the moment. I think that it's a good question. I'll talk a little more about the structure of the sun in a moment, and I think that maybe we can get back to that question. So if that's okay, I will try to put that in the back of my head, and if I forget, you guys can keep me honest later. So. All right. Cool.
Good.
Thank you.
So
let's see. Okay. All right. So yeah, actually, here we go. Structure of the sun, right? So here's a nice little cartoon that illustrates, you know, what's actually happening inside the sun. You know, so we certainly talked about the outer layers that we see, but all this stuff starts out in this thing that's labeled number 1 here. This is the core of the sun. So the core is the nuclear fusion reactor of the sun, right? This is where hydrogen gas, I mentioned hydrogen earlier, right? Hydrogen gets smashed together so strongly that it fuses into helium. And a lot of energy is released in that process. And that's ultimately the energy that we see as light and feel as heat. And it's almost all the energy that's responsible for life here on Earth. So all that stuff gets produced in the core. That's where the power source is. The second layer here you can see is called the radiation zone. So in the radiation zone, there is no energy production itself, but the energy that got produced in the core has to get through it to ultimately get to us. And this is actually really interesting because it can take 1,000 to 1,000,000 years for an energy particle, a photon, to get through this layer. Because what happens here is that, yeah, so in the core, a photon is generated, right? A particle of radiation or a particle of energy zips out, and it goes towards the radiation zone, and of course there's hydrogen all around. This whole thing is a giant hydrogen ball. So that photon will zip for a moment and then bang, and almost immediately bang into some hydrogen atom. That atom will absorb the photon, and we talked earlier about electron states, right? So the electron actually in the hydrogen atom would then bounce up a level, and eventually the photon gets re-emitted. It comes back out. But it will come out in some random direction. So even though the photon started its way towards the surface, it got absorbed and then shot out in some random direction. And that keeps happening. So the photon does not take a straight shot through the radiation zone. It actually takes a random walk. It's like a drunken walk. And it will bounce around there possibly for a long, long time until it finally, just by luck, gets to the outer layer here where we reach the 2 to 3 boundary. So yeah, so one cool thing here is that, the energy that we get today from the sun might have been produced in the core 1,000 to 1,000,000 years ago, because it took that long for the energy to actually transition through the radiation zone. Now, when we get to the outer layer of the radiation zone, we transition to what's called the convection zone. And convection is heat transfer just by moving stuff. When you're boiling water in a pot on your stove, you're creating convection within that pot, and you've all seen water bubble up. It's the same kind of thing that's actually happening on the sun, and we'll say a little more about that in a moment. Then once we're past the convection zone, then we're in the region that we already talked about. Photosphere is sort of the surface, right? Chromosphere is the innermost atmosphere of rarefied hydrogen gas that we end up seeing with our H-alpha view, through our telescope, like I showed you from the backyard. And then we're out in the corona, right? And then there are features sometimes on the sun called sunspots. I'll show you some more examples of that. These are features, on this layer labeled 4, so the photosphere. And then, excuse me. We have 5, we said was the chromosphere, with features like this one here, a prominence. And yeah, so a lot of these other parts we've met before. So let's keep going and use this knowledge to look at these pictures. So yeah, so here's a better representation of some sunspots. Unfortunately, right now, the sun is not offering any sunspots for me to show you in real time. And we'll talk more later about why that is. But unfortunately, I have to just rely on this picture from, a past year. But this is a pretty cool picture. So this is the photosphere, and you can see there's a little spot here. And then, of course, there's a big cluster of sunspots, like right here, smack in the center. And again, these may look smallish, but keep in mind, right, that the Earth is small compared to this thing, right? So, the Earth would like drop inside this sunspot. Right. And so notice, by the way, the yellow background here, it's not smooth, right? They're like little granules here. And these are important. We'll talk about these more. These are the convection zones. This is where stuff is bubbling up like the water is boiling in your pot. Okay. And actually, here's a view of a sunspot close up. So it's kind of spectacular, right? Here is the sunspot. And yeah, here is basically just really, really hot hydrogen gas. Don't touch it. Now, another interesting point, right? So the sunspot looks black, but it's actually still quite bright and certainly very hot. The only reason it looks black is because it's relatively dark. So our eyes calibrate to, this bright stuff. And, when we can see the bright stuff, this is, relatively speaking, dark enough that it appears black, but actually it's still quite luminous. Okay, and yeah, so I promised you a little better view of the granulation, the convection zones. Basically, what's the boiling water in your stovetop is instead here, boiling hydrogen plasma on the sun. This picture is from, I think, just this January. This is a very recent Science News item. So it's just an amazingly detailed picture of this granulation on the sun. And look, there's a little thing down here for reference and size, right? So yeah, and let's see. So we'll talk about miso soup for a second, and you may wonder why, right? But have you gone and had hot miso soup in a restaurant, right? So when they serve it, you will actually, next time, pay attention if you haven't before, you will see the miso kind of rise up and kind of curve around inside the water. So this is very much like the convection on the sun. And in fact, I have a short video of miso soup here. So here, yeah, you can see the miso rising from below. It kind of rises up and then kind of, moves around. That is convection, right? So there's hot stuff on the bottom. The hot stuff makes the miso rise. It gets to the top. At the top, it cools down, and then it falls back down. So yeah, so this kind of stuff is very similar to the physics, right? The action that happens on the sun. And so yeah, actually, so we just looked at the miso soup video, and here is the miso soup of the sun. Let's see. So let me show you that one. Where is that? Here we go. Okay, so here this is an animation, right, of this convection action on the sun. So this is a real time lapse of the various boiling regions, right, the various convection zones doing their thing up on the sun. And you can see this was actually pretty recent. This was from December 2019. So I think this is a really spectacular little video. All right, so we just looked at that. And yeah, again, just for context, right, for size. So yeah, here's the whole sun. You know, this square here represents the region that we just saw on the video. And then, you know, if we blow that up a little further, here's a close-up of these regions. And yeah, you can compare to like the, you know, state of Texas, for example. So these things are big. Okay, and then, so these are just photosphere features on the prior slides, right? That was the quote-unquote surface of the sun. So now again, let's take a step out and talk about the chromosphere, that innermost layer of the solar atmosphere. This is where we see that orange skin texture. Now here, it's a little more pronounced than in the real live view I showed you a moment ago, because here, the picture was taken with a lot more processing, right? So if you have a lot of time, you can pull out more detail and contrast. In a real-time view, it's going to be hard to get this kind of image, but it's the same basic thing. And you can see that these pictures were taken on days when there was more activity around the edge or the limb of the sun. So here is a pretty large prominence, right, where hydrogen plasma is erupting. Oops, I'm sorry, I accidentally clicked on that. And then here, of course, is another nice one. And you can also see some of these dark features, right? These filaments, right? These like scars on the sun. And then, yeah, so here is a slightly different view or a different picture of the same thing. And I really like this one down here. Here you can see how, you know, something that looks like a prominence because it's on the edge, but you can see it transitioning into a filament, right? So you can see that these two are the same thing. It's just one on the edge transitioning into an extension that's within the disk of the sun. So these scars, these filaments, are 3D structures that are sticking out, you know, towards us. And yeah, the detail within the orange skin of the sun here is pretty amazing. Here's that picture again that I showed earlier. This was a quickie picture I took back in 2017, and now we can maybe appreciate this a little more too, because you can see this W shape here. This is one of those filaments. It's a really long eruption, and I think you can, now that you know what you're looking for, you can probably see that this has some 3D structure to it, right? This is raised from the surface of the sun, or yeah, the outer layer of the sun. And of course, here is a little prominence sticking out. So let's take another quick trip to the backyard and see if things have changed any there. The view will sometimes get better, sometimes get worse, because the sun is changing, the sun is turning, the atmosphere is changing, right? So let's just see if there's anything new that we can make out. So we still have these little prominences here. Let me pull this over a little bit. So the telescope's not moving that fast, because if it were, then we would easily lose what we want to look at. Here we can try to turn up the exposure a little bit. Yeah, so again, we have these little prominences here. Okay, let's see, I guess we still have, yeah, the filament's still there. Okay. Yeah, not that much has changed, I guess, since we looked last. Yeah, here's still that filament. But again, maybe now you can appreciate this a little more, right? So imagine this thing right here as a raised structure, right? It's actually sticking out into space. It is essentially a prominence just within the disk of the sun, not on the edge. All right, we'll visit this again a little bit later. Okay, so since the real sun today is not offering a lot of exciting prominences, hey, let me show you some cool ones from years past. So here, this is kind of a spectacular image. Look at this thing over here. Kablooey, right? There's this really amazing prominence sticking out. And of course you have some, you know, relatively speaking, smaller ones. I keep hitting extra keys today. I have fat fingers. There we go. Yeah, so you can see there's really big one with some, you know, relatively smaller ones over here, and lots of active regions also kind of within the disk of the sun. And there's actually this really cool video here I'll show you where there's a time lapse of one of these prominences developing and then falling back to the surface of the sun. So this is from 2012. And, you know, as it's labeled here, it's a medium-sized flare, so keep that in mind because it'll actually look pretty big. So you can see that something is developing, you know, was it developing over here, and now we're going to zoom in on that. Yeah, here we go. So things are just about to start. So all this activity that you're seeing is driven by strong magnetic fields. So a strong magnetic field is pulling hydrogen plasma, charged hydrogen atoms, away from the outer layers of the sun off into space. It's very energetic, right? So it's very bright. And it's starting to look like a loop or an arc a little bit, right? But you can also see stuff raining down, right? So most of the time, these prominences, yeah, stuff is being pulled away from the sun, but then gravity of the sun will ultimately pull it back down. Although, like we said earlier, sometimes there's a really powerful release of energy, and then that would be a solar flare, right? But most of the time, yeah, they come up, and they get pulled down, and it ends up looking like this amazing rain of fire here coming down from this nice arc of a prominence. And yeah, you could probably shoot the Earth right through this, through this arch, right? The Earth is pretty small compared to this. So I think this is just a really neat, kind of amazing looking video. All right. And yeah, so let's take a moment here and talk about some eclipses. I don't know if any of you had a chance to see the eclipse we had in 2017. If you have, congratulations. I bet you it was cool. If you haven't, maybe plan on seeing the total solar eclipse that's going to be traveling over the United States in 2024. I believe it's going to start over Texas and then go up to the northeast. So it's definitely worth seeing. So here is an example of a picture of a total solar eclipse from 1999. And one of the cool things is that, yeah, so here the moon is blocking out the bright disk of the sun. And so now all that glaring light from the disk is blocked, right? And it's not drowning out all the other interesting stuff that's going on. So when the disk is blocked like this, all of a sudden you can see these prominences without having to employ a hydrogen alpha filter. So just through binoculars, properly protected if need be and all that, right? But just through regular telescope equipment, you can all of a sudden see these prominences here, and it's amazing. I was blown away when I saw this for the first time during the 2017 eclipse. The moon covered the sun, we reached totality, and it's like, holy cow! The prominences that popped out were pretty amazing. And in fact, this is a picture I took. This was just a lucky shot. I had the iPhone held up to the eyepiece of the telescope, and here the moon was just receding. So this is actually a time when you need to be careful when you look at the sun, because the sun can very quickly become too bright to the point where it will damage your eye. But yeah, so here the moon was just receding, was just pulling away from the sun. The sun was starting to be exposed. But you can still see this prominence here without really any special equipment. So pretty cool. And then here's another total solar eclipse picture from almost 100 years ago, a little more than 100 years ago. And one, it has just this really huge prominence here. So this looks like a handle. It looks like you got a handle on the sun. You can just pick it up and carry it away. But this picture is also interesting for a different reason. It has very historic significance. Turns out this picture was also used to help demonstrate that Einstein was really onto something when he proposed the theory of relativity, right? Relativity makes a whole bunch of predictions. One prediction is that light is actually bent when it travels past a massive object. So for example, if this is the sun and there's a light beam coming down, the sun would actually bend that light beam around itself like this. And so this total solar eclipse was used to help demonstrate that is in fact what happens, that this prediction of relativity is really true. So it's a cool picture, and it has some interesting scientific significance. Here's just another cool solar prominences. Look at this. Boom. It's huge. Here's another one of those giant handles. It's just spectacular, right? And again, imagine the size, right? The Earth is tiny, tiny, tiny compared to this huge loop. And then this one is probably one of the most spectacular ones here, right? So again, a giant, giant arc. And in fact, let's see, we have some video of something like that. So let's run that. And as you can see, so these are things that you can just find on YouTube, right? So this is the NASA Heliophysics division, and they publish all this stuff. Our tax dollars pay for the science, which is very cool and very useful. And you can, look at some of the results of it yourself if you want to search for them. Yeah, so here again we have this fall. And notice that here, it's not all falling back to the sun. So here, some of the material is actually ejected off into space, right? So this is a more powerful event than the nice loop that was raining down from earlier. Yeah, so I think this is also pretty slick. Okay, should we take another quick break for questions? Let's see. Anything pop up? Nancy, I think you may be on mute. I cannot hear you if you're talking.
Can you hear me? Sorry about that.
Yeah, there you are.
I clicked
Thank
the
you.
wrong button.
No problem. Happens to me all the time.
So I do have a few questions collected.
Great. Okay.
First one from Roger. And the question is, how long does the photon bounce inside the sun before escape out to reach Earth 8 minutes later? I think you touched on that in a way.
Yeah, right. So I think most of the time it would spend going through that radiation zone, right? And I've heard numbers anywhere from thousands to millions of years. And it is a drunken walk, right? So it is a random thing. I read about these every now and then, and my brain is terrible at keeping track of numbers. But yeah, it's a pretty big range because some photons might get lucky and get more or less a straight shot through, and then hey, you can get through there in 1,000 years, or you might bounce around for a long, long time, and then you're on the order of millions of years to get through. So yeah, somewhere within that range, which I realize is a really big range. But once you've made it through the radiation zone, through the convection zone, that's basically through heat transfer, right? You're just convecting upward, and like you mentioned, I think so. Once you're at the outer surface, the photosphere, pew, right, then the photon will just go off, and it'll take about 8 1/3 minutes to get to us here on the Earth. Yeah.
Okay. The next question I have is from Raymond, and Raymond asks, what zones do the heavier elements reside as fusion byproducts?
Okay, interesting question. So our sun is still, is a main sequence star. So our sun is mostly fusing still hydrogen into helium, right? Now, of course, over time, the helium will accumulate, right? You'll have more and more helium to the point where there's not enough hydrogen anymore in the core of the sun to fuse. Actually, this stuff gets pretty complicated. You end up with let's see, how can I answer this quickly? I'm not sure if this will be a satisfying answer, but I'll try. So you're converting hydrogen to helium. The helium kind of hangs out there, but the sun is still mostly 90. I forgot the number. I think we have it actually somewhere in our question list, Nancy, if I remember correctly, right? I think the sun is still like 98% hydrogen today, or something like that. It's still mostly just a giant ball of hydrogen.
I believe so.
I'm sorry, I forgot the number right now because, like I said, my brain is bad with numbers. But yeah, so over time, what would happen is you would get more and more helium, right? And at some point, then what happens is that, so helium is not as easy to fuse as hydrogen, right? So hydrogen fuses relatively easily. That's how the sun makes energy most of the time. At some point, when helium becomes too abundant, right, then the fusion reaction will actually slow down, which will cause gravity to kind of then win a little bit. So let me take one step back, I guess, to say that. So on one hand, you have a ball of hydrogen, and gravity is trying to pull that ball of hydrogen together and crush it into an even smaller ball, right? So gravity is fighting to get the sun to basically be crushed into a tiny, tiny spot. But then through that crushing action, that's what ignites the star. That's what starts the fusion reaction. And the fusion reaction is generating energy and heat, trying to blow the star up in a way, right? So our sun and other stars sit there as a delicate balance between gravity trying to crush it together and the fusion reaction trying to blow it apart. And they sit there maintaining this balance, this delicate dance, for billions or even longer times sometimes. It's amazing, right? But so when we run low on hydrogen, eventually the reaction will first slow. That will cause the star to contract, crush it together more, to the point where then, maybe helium can ignite, right? And now you can do helium fusion. And then the star may actually burn hotter. So this gets complicated, where the star will actually burn in shells, where, you don't necessarily get all the fusion reaction in the core, but you get it around the shell. And then as the stars age, they actually expand outward, But our sun will eventually die in something that's called a planetary nebula. That's a really confusing name. But when that happens, what will be left is something called a white dwarf, which will be essentially the collection of the fusion products, which will be largely hydrogen and carbon. Oxygen and carbon. So when our sun expires eventually, there'll be something called a white dwarf left. It'll be an inert ball of largely hydrogen and carbon left in the center, and those will be the ultimate, leftover fusion products of our sun. Larger stars will go through something called a supernova explosion. They make even heavier elements, and they blow that off into space eventually. I don't know. So I hope that was a somewhat satisfying answer, but we could easily spend another hour probably talking about that. It's really cool. So.
Okay. I do have two more. How about we just stick with answering the questions as opposed
Sure,
to...
we can do that. Yeah, if we got plenty of questions, we can spin the wheel one more time later, or we can skip it for now. Yeah.
Yeah. So this next one is directly, this is specifically for you, okay? Marianne's asking this question here.
Okay.
She said, I was amazed at the latest news about why Betelgeuse decreased in visual magnitude. Gigantic sunspot. So she'd like to know what's your take on this.
Good question. So actually, gigantic spun-spot. I haven't even heard that one, honestly. Maybe I'm behind a little bit. But right, so maybe to give a little more backstory for our other audience members here, right? So Betelgeuse is a star part of Orion. I actually showed it very briefly earlier when we looked at the sky in Hoagie Park. Right, so right now, Betelgeuse and the associated Orion constellation is in the daytime sky, so we really don't see it because the sun washes it out. But in the wintertime, it's out there in the night, and it's very recognizable. Once you've seen it, you cannot unsee it. You'll always recognize it. And so Betelgeuse is a red supergiant. It's a star that is... let me back up one more. Most of the stars, when we look at the night sky, right, other than our own sun, all those stars are basically pinpricks, right? They're so far away that we really see them only as tiny little point sources of light. They don't really seem to have any size. Of course, we know that they actually do because we showed you that size comparison earlier. But Betelgeuse is actually, it's about 400 light years away, I believe, right? So it takes light from Betelgeuse 400 years to get here. Don't quote me on that number, but I think that's correct. It's at least the right ballpark. And it turns out if we point the Hubble Space Telescope towards Betelgeuse, even though it is so far away, Betelgeuse is actually large enough that we can image it as something that has size. It's actually several pixels wide in the image that the Hubble Space Telescope can take. So even though that star is really far away, it's actually really huge. It is a star that will supernova at some point. It will blow up and it will make an incredibly bright dot in the sky for probably about a week or so. And that could happen anytime in astronomical terms, which means it could be in 1,000 years, who knows. But it's right around the corner in terms of the lifetime of a star. And so so Betelgeuse is a very prominent star. It's very bright. It's a red supergiant. It's really huge. If we put it where the sun is, we would be inside it, and even Jupiter, I think, would be just inside it. So it's really big. And the news last year was that it seems to be dimming, right? So we were actually seeing less light come from Betelgeuse. Like, well, that's weird, right? What's going on there? And of course, there's always some people say, hey, maybe it's aliens. Well, it's probably not aliens, though. So usually when we think it's aliens, we later find that there's a perfectly natural explanation. And what I thought I had read on this one most recently, but maybe I've missed something, is that was just, we thought that, okay, maybe we detected that there was a dust cloud or something that moved in front of it, and that was causing the dimming. So the star itself was not dimming, but something was obscuring the light. But I think you mentioned a sunspot earlier, which actually I had not heard. So I may actually not be up on the latest news here. That was a long explanation to tell you I don't know, I guess.
But that's such a good narrative you just gave.
Thanks. I hope that made sense, at least for what I did know, yes.
I thoroughly enjoyed that.
Okay.
So I do have one more.
Okay.
This one goes back to the slide on the total eclipse in 2017.
Yeah.
Okay. Raj asked that, was it taken from orbiting telescope?
Oh, okay. The 2017 picture, the one I took, no, that was from Oregon, actually. I had visited Oregon, and I had a 100 millimeter just white light telescope set up, and with my iPhone at the eyepiece. That's it. That was the 2017 picture I showed. Yeah.
Oh, you took that.
I took it. Yeah, the 2017 was actually my picture. It was I got lucky taking that shot with an iPhone, and hey, you could get that lucky too. So, like I said, if you haven't seen one of these events yourself, go check it out, and you could even take some images like that yourself. Although, just a quick note, so that was my first total solar eclipse, that one in 2017. There were 2 minutes of totality. That means that for 2 minutes, the moon was completely covering the disk of the sun. And everybody tells you, that goes really fast. Don't fool around. Enjoy the 2 minutes, because if you get distracted, it'll be gone like that. And they were right. So, for your first solar eclipse, don't necessarily plan on taking pictures, because you may actually miss it, because you end up fiddling with your camera or something. So just keep that in mind if you do experience the next solar eclipse as your first one.
Yeah, I did get to see that solar eclipse, and it was spectacular.
Mm-hmm.
So here I have one more little thing.
Okay.
A little remark coming back from Marianne.
Mm-hmm.
She said that what she said about the gigantic sunspots,
mm-hmm.
that was from the findings published in the Astrophysical Journal letters.
Cool. Thank you, Marianne. Yeah, so I'm not always up on everything either, so thank Marianne. I really appreciate that. So I just learned something too. I like it. Thanks.
Yeah, someday I can look into that as well. Thank you.
Yeah.
Thank you, Marianne.
Yeah, that could be another future, science, solar science topic, just, for our topic of the day slot that we're going to start having here. So something to keep in mind.
Yeah, those are some very good questions we have.
Yeah, I really appreciate that.
Mm-hmm. Yeah, with that, you know what? I think I'm going to skip my Q&A. I'm going to just hand it right back to you.
Okay, let's do that. Yep. That's
just
cool. So,
continue on.
sure, let's see. So I didn't want to show maybe just a snippet of a video here. We can just take a moment and look at this because again, I just think these are cool things to look at. So this is kind of a compilation of,
has shed light on our home for over 4 billion
again,
years.
put together by NASA Solar Dynamics Observatory, and you can just see, activity on the sun. This is all time lapse. So usually a prominence will last for hours to days. So when you see like the looping rain we showed earlier, those are time lapses, right? So it's not real time. It doesn't go quite that fast because, of course, these things are also really, really big. But the sun is quite active. And sometimes, especially on active days when we look at the sun through our H-alpha scopes on the Earth, we can detect change within the couple hours that we would do a solar Sunday event because these things change, the prominences themselves move, and the sun rotates. So, yeah, so we can detect change just in an afternoon, but these things you see in the video, they are time lapses. But again, the different colors here are mostly false color, stuff our eyes could not see. But we use instruments to make these colors visible to ourselves, and they reveal a lot of activity and detail, which is very cool, I think. Yeah. Yeah, here's that guy again that we saw earlier. So this one is just a spectacular event. All right. Let's see. So we didn't ask you any questions, so you don't have to give any answers. So we'll talk for a moment then about the solar cycle. So this is actually really important to help explain why today we're having a hard time hunting for interesting features on the sun. The sun goes through an 11-year cycle, and here's a representation of a prior cycle, which started in 1996 when the sun was relatively quiet. Then, through the years, it became really active with lots of, interesting features, and you can certainly see variation, hot regions, bright regions, and then it gets boring again. In 2006, that cycle ended. So let's talk for a moment about what's going on with this kind of a solar cycle. Here's a graph of the same kind of thing, right? So here, there's a little, science here in terms of a graph. The wiggly line is kind of a sunspot count, so people count sunspots. That's an indication of how active the sun is, and then it was kind of averaged out into the wavy line. And so we can focus on cycle 24. So the last solar cycle started around here, right? 2009, 2010. You can see here is a minimum, right? That means here was the least solar activity, and then things got busy, and the sun was very active. And around this active time, actually, there were some really big sunspots. I remember one day where there was a sunspot large enough that you did not need a telescope to see it. You have to wear eye protection, of course, right? But as long as you wore eye protection, you could just look up at the sun. It's like, hey, there's a giant sunspot on it. And so we could see that kind of stuff back in 2014. But now, look at where we are, right? Here's 2020, and we're right where this curve is bottoming out. So we are at the solar minimum when the sun is not very active. And that's why we're having a hard time finding some of these interesting features that we see in pictures of years past. So let's talk about that for a moment. What's going on here, right? So this is all about magnetism. The sun is mostly hydrogen plasma, which means it's a tremendous soup of protons, hydrogen nuclei, and electrons. This is all hot and mushed together. And as this charged soup moves, it moves in through two ways, right? Through convection, the boiling action, we talked about that. And it also moves to something called differential rotation of the sun, and that we have not talked about before. So let me tell you what that's about. So here's a diagram of the sun. If you think back to the Earth for a moment, right, of course the Earth is spinning on its axis, right? That's what gives us our day-night cycle, right? So it takes about 24 hours for the Earth to make one rotation. And because the Earth is rocky, right, the Earth is basically a ball of rock, the rotation is the same no matter where you are. You could be standing like here on the Earth, if it were the Earth in the picture, and it would take you 24 hours to go around, or you could be at the equator and it would take you 24 hours to go around. But the sun is different. The sun actually has different rotation rates depending on where you are. So it's kind of sloshing around. If you were standing, again, you can't stand on the sun, but imagine for a second, if you were standing like up here near the pole, it would take you 35 days to go all the way around for one rotation of the sun. But if you were on the equator, hey, it actually takes only 25 days. So it turns out the material, because the sun is a gas ball, basically, it's a sloshy ball, not a rock. Turns out that the equatorial region actually moves faster. And so this is what's called differential rotation. It's not all the same rotation rate depending on where you are, along the latitude of the sun. And so what happens here is this. So imagine you're at a point where everything kind of lines up nicely, right? So everything was kind of in a clean starting point. Now the sun is rotating, but we said that things actually rotate a little faster on the equator. So that means over time, right, the center stuff, the equatorial stuff, gets dragged along faster, right? So here we had slower rotation, and then the rotation here is faster, and so things get twisted. And if you keep going after several rotations, yeah, all this stuff gets twisted almost like a spring, right? And so yeah, so as time goes on, it gets, you know, more and more twisted up, and that is this differential rotation. And so what's happening is, yeah, so here at a solar minimum, turns out everything looks relatively clean, more like it does over here. And then as time goes on, oops, again, my fingers seem to be click happy today. So as time goes on, we reach the solar maximum, where we've reached kind of maximum twistiness, right? So the more twisted things are, the more complex the magnetic fields become, and the more active the sun is, the more prominence it generates, and the more sunspots you have. And then these things kind of unwind again, right? And we end up back towards a solar minimum. And like I said, this is all about magnetism, right? So here, these are diagrams you may remember from high school or so, right? So here's a bar magnet, and you have magnetic field lines, you know, between the north and the south pole. And you may have even done an experiment or seen it where you can put a bar magnet underneath a piece of paper. So here's the bar magnet underneath a piece of paper, let's say, and then you put iron filings on top of it, and you can kind of jiggle it, and you can actually see the iron filings aligning themselves to the magnetic field lines, right? So this is you can do this experiment yourself. It's a visualization of the real magnetic field lines, you know, of a bar magnet. Now, a bar magnet is a static thing, right? The magnetic field is always the same. It just sits there. But it turns out that things get more complex on the sun, right? So when you have moving charge, like the moving protons and electrons of the hydrogen plasma, that motion creates magnetic fields. Now, and magnetic fields, in turn, can affect how charged particles move. So there's a lot of complex interaction up there, right? And so as a result of these complex magnetic fields and these interactions of magnetic fields, moving charge, and moving charge, changing the fields, you end up with situations where, yeah, locally the convection can slow down, and that causes sunspots, right? So we said the sun is boiling up, right, through the convection layer, but sometimes strong magnetic fields will slow the convection in some spot, and that's where that region becomes actually a little cooler and then ends up appearing black, right? So sunspots are places where the convection has temporarily been suppressed. And then in other places, the magnetism can drive the prominences, like we saw in that beautiful loop that then rained down, right? And you could see that loop, yeah, that the plasma was following magnetic field lines. It looked almost like we saw on this bar magnet picture on the prior slide. And so here's an illustration of the sun's magnetic fields, right? So the Earth, of course, has a field that's very clean, north-south, a lot like the bar magnet. But look at this, the sun here is a mess, right? So of course, these magnetic field lines are not directly visible, but they were extrapolated by, you know, a computer model based on actual measurements, right? So this is a representation of actual magnetic field lines, and you can just see it's a giant old mess. This is from 2016, and here is a different time. You know, 2018 looks very different. Right, so this is changing all the time. And during a solar minimum, it's relatively clean and organized. And during a solar maximum, it's just an even bigger mess, right? And the bigger the mess, the more interesting activity we get to see. And yeah, that takes us kind of to our last question break. Did we collect any more questions?
I actually don't have any questions for this segment, and I think I'm going to save my questions for the next event.
Okay.
With the time that we have left here, would you like to introduce our next segment, Wolf?
Okay, so what we can do is, we'll one more quick visit to the backyard, because in a moment the sun will probably end up behind a tree that's out there, and I want to take one more look before the tree deprives us of our view. So give me 1 second here. Let's do that. Where's my button? Oh my God, I lost my button. Here's my button. There we go. Okay. Yeah, so here we're back in the backyard. Okay. Yeah. So again, I think we saw this guy before, right? Down here, you can see there's that little tongue sticking out, right? So that's a small prominence. Yeah, that's kind of what the sun is offering us today. I'm afraid none of these big, spectacular things that I showed you in the pictures. I think we're still seeing. Yeah, we can see something here, right? Maybe again, one more time, we can try to see if I can just pull it out maybe a little bit more. So what I'm doing is I'm turning the exposure up a little bit. So I'm making the camera basically sample a little more slowly, collect more light between each frame. If anyone does photography, you know what I'm doing. I'm basically keeping the shutter open longer, right? And that's of course making the disk of the sun brighter, but it's also helping us see this a little bit better, although it's kind of hard to see today. Yeah, but so we do have a little bit of problems activity here. I think we saw that before. So unfortunately, nothing particularly new popped out, or it didn't improve. But let's make one more visit to the... Hey, maybe I could tell you guys this is a sunspot, but I guess you wouldn't believe that because it stays in the same place, and it's probably really just dirt on my optics somewhere. So, yeah, okay, here's the filament that we saw earlier. Okay, it's still here. Unfortunately, it hasn't crispened up or anything else. Again, this is a prominence that's arcing towards us. And down here, you're starting to see the tree, right? So a moment ago, you saw some shadow appear down here, and that's the sun about to drop behind the tree. All right, okay. Yeah. Let me take one more quick look at the top here and see. Yeah, again, yeah, I think we saw this earlier too, right? There's some wispy structure here, very faint, thin prominence. We can pull it up a little bit more. Yeah, there, right? But yeah, so now this disk of the sun is super bright, but now, yeah, we can see a little more that, again, there was something here. We saw this guy earlier. Okay, looks like that's what the sun offers us today. Let me, but before we go into our final segment here with Emery, I wanted to quickly, so we just checked the live view, and I wanted to quickly show this video. So this really highlights what's happened over the last 10 years. Don't worry, we're not really going to look at 10 years. You can look at the entire 10 years by finding this video on YouTube. So the whole video runs about an hour, but I've clipped out a few things that are just interesting to us here. So this is back in 2010, shortly after the last minimum. You may remember the graph that I showed you a little bit ago. So here the sun is relatively quiet, but you can see that there's certainly stuff going on, right? There are bright regions, and you can see some of these magnetic fields in action, right? And yeah, so this was relatively quiet after the last minimum. And in a moment here, what we're going to do is we're going to transition forward by 4 years. We're going to jump to 2014. There you go. And this is around the last maximum. And here you can see, yeah, there's a lot more going on. It's very obvious, right? So a lot more bright regions, a lot more activity, you know, lots of magnetic field lines. You can see all this arcing going on, right? It's very, very complex. And actually here is this giant sunspot. So here is one of these huge sunspots. I think this is the one that I was describing earlier that I could see with, you know, protected but otherwise unaided eyes, right? Yeah. So this was 2014, very busy. Solar Sundays there were great. And now this is in May of this year, and look how smooth the sun is, right? It looks like a big cotton ball, and this is what we're dealing with today, and that's why it's so hard to find interesting features in the real-time view today. So, hey, you guys get what you pay for. This is the sun today. You know, maybe next time we get lucky, there's a little more. Like, for example, here was one feature. You know, if we had looked at just the right time, we could have seen this through our hydrogen alpha scope. But of course, you know, this may have happened while we were all at work. I don't know. But yeah, so I really like this little video. It really highlights the contrast of, you know, what's happened from last solar minimum or just the end of the last solar min to that max and now to today. So, all right. Okay. Yes, Nancy, go ahead.
Throw in a little bit something here.
Okay, please.
This is not a solar direct question, but it's about your telescope.
Okay,
Raj
sure.
asking that, do you leave your telescope set up in the backyard or take it inside every night?
Good question. So no, I don't leave it set up. Yeah, I take it indoors. It's not sufficiently protected, right? And I wouldn't want it to sit out there all the time. And I'm really not in a good place to have a telescope in the yard. I have too many buildings around. I'm lucky that I can look at the sun during the summer. During the winter time, I'm going to have a hard time running these events from home because the sun will be behind buildings. So we'll see what happens as time goes forward. I hope we can go back to Hoagie Park where we can, you know, look at this stuff more directly. So short answer, no, it's not outside all the time. I just take it out for these kinds of events. Yeah. So I set this up just for you today. Okay.
That's
Any
all I
other
have.
questions? Okay, thanks.
That
So
was
then,
the
yeah,
last one.
so let's jump to our quickie science topic. That'll be kind of our last segment for the day, and this is where Emery's going to talk to us a little bit about some special topic for the day. Okay. All right, Emery, you have the floor.
All right then. So hey guys, my name is Emery. Is the voice coming through as well?
Yep, looks
Sweet.
good.
You checked. All right. Then. So I'm a senior at Palo Alto High School, and I'm an avid astronomer like you guys. I'm pretty excited to be here, and I hope to add a little bit of spice to the normal presentation by going over some recent heliophysics research, which is basically the physics of the sun and its interaction with our solar system. So the focus of today is a new paper published by the Rochester Institute of Technology, particularly Amber Dubell. So what we see here on the left side is the paper itself, and the focus of the paper is actually utilizing diffractive solar sails for satellites orbiting the sun. So you can see an example of it in the bottom right of the screen. That's the actual solar sail they're experimenting on. And we'll go in depth into what exactly these are and the implications of this research. So next slide, I guess. Yep. So first of all, what are solar sails? So solar sails can be seen in the same light as modern wind sails. But instead of using wind, we are using the photons, which are basically the particles that make up light to push our craft. So here you can see a diagram showing exactly how this occurs. So you have a particle of light going out from the sun, it's the incident, bouncing off the sail, which is that black flat line, our solar sail. And using some well-known laws of physics, we are pushed in the direction of the net force, which is in the bottom right of the diagram. Now, why would we use solar sails instead of other forms of propulsion like we always use, like chemical thrusters? So the issue with chemical thrusters in particular is that they require fuel. They're very efficient and very powerful, but you need these large amounts of fuel. That's a big issue, actually. Like a large amount of the spacecraft, rockets, a large part of mass is fuel. And same with satellites, you have a lot of mass gone to the thrusters themselves and the systems that maintain them. But with solar sails, we're able to remove all of this and basically replace all of it with like a single flat sheet of metal. And we have a continuous form of propulsion by the sun, which shouldn't be running out anytime soon. So we can replace all of this. It greatly reduces the total weight. So by reducing the weight of the spacecraft, we can actually greatly increase the total speed that we can accelerate, and we can reduce the cost. And we don't need to bring all this fuel and all this expensive equipment with the thrusters. That's solar sails. So now we'll go into what diffractive solar sails are. So solar sails have long been researched. In fact, if you're a Star Trek fan, there's a Deep Space episode, Deep Space Nine, that features a solar sail ship. It's pretty interesting, actually. But these all use the idea of a reflective solar sail. So that's what I talked about previously. And it's a simple idea of you have a photon, it goes towards your flat sheet of metal, it bounces off, and you're propelled in a certain direction. However, the issue with these is that they need to be tilted at an angle, because you have the law of reflection, it bounces off, and it's some fancy combination of the forces involved, and you get the angle, the force direction that you desire. So instead, scientists have come up with the diffractive solar sail. So this utilizes diffraction, which is a complicated and interesting process of itself, but essentially means that instead of having to tilt the sail, we have here a diagram showing that you can face the sail exactly towards the sun. And utilizing diffraction, we get a force that's basically perpendicular to the sun line, the direction of the photons being emitted, and you can see it as a dashed line here. And you get a force that's basically perpendicular to it. So you can see in the top right of the diagram. And that means we can have much greater efficiency. It's basically all the force that we're getting from the photon is being converted into the momentum transfer. So we're getting all of that push from the photons being to push our spacecraft in desired direction, which is much more efficient. We like this a lot more, rather than having two people push our spacecraft at opposite directions, and we get a meager, tiny little force in the direction we want, where we have one person just with the force of both people pushing in the direction we desire. So as you can see, it'd be much better. Secondly, reflective solar sails. So it's basically utilizing photons that are bouncing off our flat sheet of metal. So with this, we have the adverse side effect of some of the photons are actually being absorbed by the metal. So, if you leave metal on the sun, it gets really, really hot. Same principle here. So it's absorbing some of the light, and this greatly increases the temperature, and this can be a big structural issue. So you can have an overheating. So instead, with diffraction and diffractive solar sails, a much smaller percentage of the light is absorbed, and we can avoid this actually pretty serious issue of overheating. So a lot of space equipment needs to be super cooled. So without this issue of like the sun itself is a massive furnace with fusion processes, and by not having it kind of transfer all this heat into our spacecraft, that's a very, very good thing. Finally, if we continue on to the last part, so what are the implications of research? So why do we like solar sails? Why do we care about diffractive solar sails? So we know they're better than normal solar sails. So what exactly will we be using them for? Well, the specific use case for this paper was detailing near-sun satellites. So I believe, as Rajul was talking about orbiting telescopes, we can actually have satellites that begin to orbit the sun utilizing these solar sails. Rather than having like costly maintenance, we had to put a normal satellite there. It'll need to use these thrusters, push itself, very short lifespan because it only brings so much fuel. We can just put a solar sail satellite there, and because the sun will essentially be here for the entire lifespan of the satellite, it can just propel itself. And so that's a very interesting idea, in that we can construct large amounts of satellites, begin studying the sun much closer, and get a lot better advances in the heliophysics than we currently can. A second interesting use for this, the idea of utilizing diffractive solar sails for Earth satellites. So because they're much more efficient than normal solar sails, the idea of solar sails, you can use a laser to kind of push it up. It's not that powerful though, because remember, you have to tilt it at an angle, so some of the force is lost that you're utilizing for a laser. Same idea of photons being like sent out by some source. Here's some laser on Earth, it could be the sun. But now with diffractive solar sails, we can use a higher percentage of the force and energy being transmitted by this laser to keep our satellite in orbit. So it's now a very real possibility of having satellites orbiting the Earth that are utilizing solar sails instead of normal conventional chemical thrusters. So kind of overall, solar sails have been long theorized for propulsion. With this research, and potentially more like in the future, expect to begin hearing about more and more satellites using solar sails to begin sailing around our star system with diffraction.
Cool. Yeah, thank you. So I think solar sails are a cool topic, right? I remember reading about them a long time ago too, when I was a kid, right? Reading about sci-fi stuff or space science stuff. And like Emery mentioned, a really big problem of sending stuff out into space is that, the fuel costs a lot, right? You've seen rockets launch, and then the payload, the capsule sitting at the top, everything below it is basically fuel, right? So if you didn't need that much fuel to maneuver, that would be a huge gain. So solar sails offer one of those, potential alternatives. Now, solar sails are not going to give you a lot of thrust, but they give you very consistent thrust, right? And this is where, I like this idea of maybe having little craft with solar sails, and we can use lasers to push them. And with that, we could possibly even, people have done some math and theorized we could maybe even send a craft to the neighboring star system that we said earlier, Proxima Centauri, for example. It would take a long time to get there, but you don't need a craft that carries its own fuel. You can push it, with lasers and through solar sails. So that's kind of cool stuff. Yeah. Thank you. Thanks, Emery.
So, Wolf, I do have one last question. Can I squeeze it in?
Okay. Yep.
Okay, one last one. This is coming from Bill. What's the difference between a solar prominence and a solar flare?
Okay, sure. Yeah, we can quickly review that. Right. So a prominence, we said, is you have the sun, right, and you have strong magnetic fields pulling material away from the quote unquote surface of the sun into these loops or arcs, right? Those things are prominences, and many times prominences will then just kind of fall back down under the force of gravity, like that looping rain video we saw earlier. So that's just a prominence. And remember, a filament that's within the disk of the sun is the same kind of thing as a prominence. We're just seeing it from a different perspective. But then a solar flare is what a prominence might turn into. So you could have a case where, yes, so you get a prominence, you have the sun here, a prominence develops on the sun, and now you have an abrupt, really fast reorganization of the magnetic fields. It's like a rubber band snapping is often an analogy. And I know that's kind of hard to visualize, basically, but what happens, though, is that, so the magnetic fields that was pulling this prominence abruptly reorganizes, changes shape, changes strength, and as a result, energy can be blasted off into space, typically in the form of electromagnetic radiation, right? So strong electromagnetic waves will be shot off, and that would be a solar flare. An even more powerful event is something called a CME, or coronal mass ejection. That's when you actually have hydrogen particles, right, mass from the sun, not just photons, but physical mass particles blasted off into space. And so these are very powerful events that happen every now and then, and we don't want to be in their path. Every now and then that does happen. There's something called the Carrington event. I always forget the date because, like I said earlier, my brain is bad with numbers. But we had something called the Carrington event around the time of the telegraphs. So when the telegraphs were in use, there was a really strong energy eruption on the sun and a coronal mass ejection. The stuff was blasted towards the Earth, and that induced electricity in the telegraph network, and it caused damage, and I think it even injured or maybe even killed somebody, right? And today, our technology is much more reliant, of course, on electronics. So we are worried about, a really strong coronal mass ejection, a really strong event from the sun blasting out and heading towards us. Most of the time, they go into empty space, because space is really big like we saw. But just by chance, they can go towards us. And if it does, we want to have warning, because if we know it's coming, we can take countermeasures. And that's one reason why people study the sun. And there are people who are studying solar weather to try to predict these things so that we could take countermeasures if something like the Carrington event were to happen again. So prominence is basically just a loop that develops. It might rain back down. A solar flare, it starts out maybe as a prominence, but then there's a dramatic shift in the magnetic fields, and energy is blasted off into space. And the next level up would be a CME, or coronal mass ejection, where actually material from the sun is also blasted off into space. I hope that made sense. So.
Yeah. Just to complete your answer, Wolf,
sure. Yeah.
The Carrington event took place on 1950. In 1859.
18, yeah, okay. There you go. Thank you. Yes, I always forget these dates. I appreciate you helping me with that. Thank you. So, okay. So let's see. So, yeah. So I'm curious, before you sign off, I'd be curious to find out, what did you find most interesting today, or was there anything that was really surprising? Because again, we rely on your feedback, and I try to learn from you guys. I'll look at the YouTube chat later, and I try to learn from you guys so we can make these events better going forward, because we're learning how to do this. We're all new to this online world as we're dealing with COVID-19. So yeah, if you don't mind, tell me what you liked about today, or again, if you have feedback for specific things we could do better, please let us know. Just a quick reminder, SJAA is here for you with lots of other types of events as well. Next week, Friday, I think I pitched it earlier. I'm giving another intro talk, Sites of the Cosmos, and there'll be, other events coming up. So please keep an eye on our event calendar at meetup.com or just at sja.net. Finally, I would say, if any of you is interested in helping out in learning or promoting astronomy and science in general, let us know, right? SJA can use your help in technical and non-technical areas, especially as we're trying to increase our online presence, right? We have a lot of new jobs that all of a sudden popped up that we're trying to do. And we could use your help. So if you like this stuff, if you want to help us, please contact us. Don't worry if you don't feel ready. We'll help you learn the stuff you need. So yeah, thanks. And with that, I'll just say thank you. I really appreciate your spending time with us today. I hope you found the last 90 minutes or so interesting. And yeah, please check us out for other events. And that's it. So I guess, Emery, Nancy, I guess we can say goodbye for today.
Goodbye,
everybody.
Thank you.
You guys.
Thank you. Yep. Enjoy the rest of your Sunday, everybody. Bye-bye.